following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, ready to go. Okay, so first of all, to say thank you to several people in the class who sent codes to find these wavefronts for when a shock, a step function, is moving along with velocity c. I had roughly drawn what these three methods produce, but it was much better to see it in Mr. Sikора's movie that's on the 18086 site. And sure enough, behind the moving front is a overshoot that reminds us of the Gibbs phenomenon from Lax-Wendroff, and I think it's sort of unavoidable if we have a negative, because one of the three coefficients at the previous time is negative for Lax-Wendroff. That's how it gets its second order accuracy, and we see that better accuracy in a much steeper profile. And then Lax-Friedrichs, if you noticed, has a sort of jagged profile, and I guess, well, maybe you've realized why that would be. Somehow Lax-Friedrichs is kind of operates on a staggered grid. We'll see, actually, I've drawn a staggered grid here so I can say what I mean. Lax-Friedrichs computes this value from the two earlier values there, and then at the next level again, and so forth, so that actually Lax-Friedrichs only is using two staggered grids separately. And I think, and normally with Lax-Friedrichs we call that n+1 and n+2 and n+3, but the picture is still right. So I think that's probably responsible for what you see, that there's two waves, two fronts, right, one delta x away from each other. And finally, upwind is also smeared out. I guess I was so pleased to see these actually showing on the website, and it makes me think of more questions, and maybe you too. First of all, as time goes forward, we see this bump beginning to appear. So am I right in thinking that it reaches a certain height and stays there? So that, I guess I'm thinking about sort of further questions, because every time you do a numerical experiment, good additional questions show up. And so I'm wondering, as this wavefront forms, this characteristic profile for these three methods, first of all, does that profile settle down to a steady profile? Ultimately, it'd be great to be able to predict what it would be. And in particular, does that bump reach a certain height? Because you can see it just barely forming, and then you see it growing to a certain point. And then when the movie ends, fortunately, it plots this picture, and you really see the profile. And you can actually see, if you look closely, that it goes above 1 again, and probably more. So that would be, does it approach a steady profile? Does that height settle down? Well, it'd be fantastic to be able to predict that height. And for example, you always want to know, how do things depend on the parameter? And the one parameter we have in this problem is r, c delta t over delta x. If I change r, I'm changing all the coefficients. If I changed r to be exactly 1, then the profile would be perfect, right? That's the golden ratio, r equal 1. I would be computing that value exactly from this value at exactly the right slope on the characteristic and perfection. But now as r goes away from 1, I presume, it goes down below 1. Of course, If it goes above 1, catastrophe. If it goes below 1, I presume the bump begins to appear, goes higher. I don't know. Could you see how the dependence on R appears? And then I can even suggest one more thing, which is let's put a fourth guy onto this picture, which would be leapfrog. Leapfrog for first order equation. So let me just put down below what that would be. So it would be on that kind of a staggered grid. A new value at time n plus 1 would come from these at time n, really, and this one at time n minus 1. So leapfrog would, you think of it right away. I use a center difference in time, uj n plus 1 minus uj n minus 1 over 2 delta t's equals c times a center difference in space, uj plus 1n minus uj minus 1n over 2 delta x. So you see right away, the 2's cancel. The delta x times c, delta t times c over delta x is our old ratio r. So this is easily written in terms of r again. It does have this 2 time step issue. And of course, we have to think about stability. I'm writing down a fourth candidate for the equation ut equals cux, of course. Before I come back to the second order equations or systems, I just wanted to put in these comments, partly because I'm thinking about projects that are, and I hope you are, that so some people will have like theses or problems from other courses which involve solving PDEs, and that'd be perfectly natural to base a project on. But if you don't have some specific application, then here are a whole lot of interesting questions to just go further with that. So the dependence on R would be the profile dependence on R, C delta T over delta X, would be a question. And let me just emphasize, what's the goal? When I say that this upwind one is smeared out, I mean that it doesn't satisfy what you really hope for. You want to capture that shock, that discontinuity. Well, not perfectly, you can't expect that. But you want to capture it maybe in, let's say, 2 delta x. A good method captures the shock within 2 delta x and does it without much undesirable oscillation, unphysical oscillation like that. So these are methods where we're trading off a good shock capture versus a smeared one, which is not satisfactory, really, in a lot of applications. So capturing the shock within 2 delta x, roughly, is highly desirable, and you might have to go to add a artificial viscosity that we'll discuss to get there. Okay, so that's past things, but still very much present, if I can say. And here I've introduced a new leapfrog, a one-way equation leapfrog, I'll call this, where the last lecture was about two-way leapfrog for UTT equals C squared UXX, a two-way wave equation. I might just mention about this one-way leapfrog. Once you put in e to the I kx, as we always do, or e to the I k j delta x in the discrete case. So you would put in e to the I j delta x times k, and then find the g, the growth factor in that'll depend on k, and will tell us the time dependence. So it'll be a g to the nth. I think you'll find that for this guy, the absolute value of g is exactly 1 while it's stable. Of course, if the Courant condition is violated, then there's no way it could be stable, and g's will be bigger than 1. But I think in the stable range, you will have, this g will have absolute value exactly 1. So it'll be on the unit circle, and you don't have much leeway, right? We found upwind was like well inside. Lax-Friedrichs was well inside. Lax-Wendroff, because it had higher accuracy near for low frequencies, was closer, and I think this guy is right on. So this is the first order methods. This is Lax-Wendroff, and this would be this second order method. And so you're really playing with fire there, and maybe this is not a favorite just because it's too close to the edge. In fact, right on the edge. Okay, so those are some comments really generated by your numerical experiments. And I think that's the way this course should, homeworks and projects should develop out of numerical experiments. Okay, now I'll come back to complete my lecture on the second order wave equation. So we studied leapfrog for that. I won't repeat that. But then with second order wave equation, we have another option, which is to reduce a second order equation with a 2 time derivatives to a system of 2 equations that are first order in time and space. And I've chosen to use the letters H and E as a kind of a hint that we're touching a really big application, which is electromagnetism. So E for the electric field, H for the magnetic field, but here in 1D, so it allows me just to mention that in 3D, when E has 3 components, H has 3 components, this is really the curl, and this is really minus the curl. And the notes will show the beautiful YEE mesh, staggered mesh that copies for finite difference methods the properties of the curl. Our interpretation of, and the properties of that Maxwell discovered, the physics of, current magnetic fields going around a wire along which an electric field is going. Okay. But let me stay here with one dimension. So, first of all, can we recover the wave equation from that? Let's just see that we haven't left behind the wave equation. Okay, so I just take the second derivative. So the second derivative, I just want to recover the wave equation, show that I haven't lost it here. So this will be, if I'm taking the time derivative of the first equation, so I get d second h dt dx, right? But by the useful, extremely useful fact that this is the same as taking the t derivative first and the x derivative second, now I have the x derivative of this equation, so this is c. Now I have the x derivative, or c times it, so now I'm up to c squared, the x derivative of the x derivative. Right. Okay. So we eliminated h, got back to one equation, second order, and it's the wave equation. Okay. I want to show the same thing now for finite differences. It's just, it's such a simple and useful device, and our point will be that it works for just as well for differences. And that allows us to do this staggered grid idea. So the staggered grid idea is, I'll do E on this grid, at these grid points, H at the half points, E again at the integer points, H again at the half points. And now, so my difference method, leapfrog, on the staggered mesh will copy, so the first equation will give E at the new time from the difference in H at this time, and so you see it. dE dt is going to be replaced by that time difference. dH dx is going to be replaced by this space difference. And that will determine E at the new time. So I need time 0 and time 1/2 to get started. So maybe I put those down here somewhere. I have to use the initial condition, the initial velocity, to get started on E and H, and then I go onwards. I've got to this point and this point. Then this guy comes from this one, and this one. And, of course, that similarly comes from the same equation shifted over. And then, now I know these. Now I'm ready for this one, coming from, what am I approximating now? I'm on the staggered part of the grid, the half steps. I'm approximating this on the half steps, where H is defined. So that minus that is the time difference. This minus this, which I know these now, is the space difference in this equation. And that's what allows me to compute the new one. You see, it's a simple idea. It's close but different from my scalar leapfrog, one-way leapfrog here. Here it was the same U at all the points. Here it is E at the integer time levels and H at the half integer time levels. And, well, it's natural to say, I'm calling this leapfrog. Could I do this for the difference equation? I just want to see that if I eliminate H, so you saw what happened there. By using the identity that the second derivative in t and x is always the same as the second derivative in x and t, I eliminated H and got an equation that involved E only. Well, what's going to be the corresponding identity? Trivial, but just trivial things are not bad things to notice, for the difference method. Well, here, this is what I wanted to be sure of for the h part. This h, so the h were now, do you mind if I draw yet another symbol? I want to use this idea to eliminate h. So let me put two h's there. Is that right? Yeah. I think what I'd like to know, well, let me just say what I believe. I believe that the time difference of the space difference of h at mesh points is equal to the space difference of the time difference of h at the same mesh points. I meant to put these as subscripts. It's not delta. It's not delta x, it's delta sub x. Difference in the time direction, difference in the space direction. Let's just see what this means. Let me redraw these 4 points. These are h at all those points. So this says, figure out the space differences. So this minus this, and this minus this, and then take the time difference of those. Can I see what I'll get if I do that? So this means I take the space differences. So I have 1 minus 1, and that would be 1 minus 1. But now I'm going to take the time difference of those. So that'll be this one minus this one, and this one plus this one. Do you see that? What we have here is h at this point minus h at this point minus h at this point plus h at this point plus 1. And I claim that we have the same thing here. That if I take the time differences first, can I do that? Instead of taking the space differences first, I'll take this one, this time difference, this minus this, and I'll subtract. I'm taking now the space difference. I'll subtract. Are you with me? You see it's just the same 4 values, 2 1s and 2 minus 1s. Whether we go first, in fact, this actually is I think maybe throws a little light on the calculus identity that we can exchange the order of the derivatives, because we know we can exchange the order of the differences because we've just got numbers like 1 minus 1 minus 1 and plus 1. Okay. So, and if we let the spacing, the mesh go to 0, this, and divided by the delta x and the delta t, I suppose we would prove the continuous case. So in a way, this throws light on something that's probably something that we take for granted, but we wouldn't want to be pressed on too closely. Okay, so having that identity allows me to do exactly what I did with the continuous case there and show that this, when I eliminate the half levels, I've got ordinary leapfrog. So when I eliminate half levels, when I eliminate this half level, let's say, then I'll be connecting, well, yep, when I eliminate half levels, I'm going to be connecting these at 3 levels, 1, 2, 3, and the second difference. It'll be leapfrog. It'll be so since it's been a few days since we wrote down two-way leapfrog or second order equation leapfrog, let me just write it again. And that's what we would get. The time difference squared of E will be equal to c squared times the space difference squared of E. And of course, here we have a delta x squared, and here a delta t squared. So altogether, an r squared, that's the formula we know. That's the formula we know. Okay. So if I simplify this to make it look good, put the delta t squared up there, you see that it's just r squared. And maybe it's worth realizing that, again, the magic r equal 1, the magic, so also the magic ratio r equal 1 gives the exact u agreeing exactly with u. Yeah. This equation, if r is 1, would be satisfied exactly by the continuous solution, and so it's the same as this one. Okay. So that's leapfrog. So can I summarize leapfrog? Leapfrog was, first of all, it led us to these, it worked for second order equations. It led us to the same stability condition, that r had to be less or equal 1, but it took a quadratic equation for g. Remember, we had g squared minus 2g times some quantity a that involved r's and cosines plus 1 equals 0. And the reason it was a quadratic was there were 2 time steps involved. But we handled that. We got stability. If r was less than or equal 1, that led us to a in magnitude less or equal 1, and that led us to g. I'll just remember those steps. A less or equal 1, and that led us to g less or equal 1. Okay. Yeah, the notes, including more about Maxwell's equation and Yee's beautiful method with a figure that shows his mesh, will go up. I mean, every section is getting upgraded, and this is the next one to be upgraded. Probably by tomorrow, you'll have a good section on second order equations. Anything, so that, for me, that's what I wanted to say about the wave equation alone, with no diffusion. And now I'm ready to move to the heat equation. So what do we have coming up? So maybe important to say what's coming up. So we've done one-way wave. Now we've done two-way waves. Next comes the heat equation, heat diffusion. And then will come a mixture of the two, convection diffusion, and by the way, so I'll go straight to these. In a couple of weeks, we have a guest lecturer who will do the applications to financial mathematics, mathematical finance, specifically the Black-Scholes equation. So you probably know that a lot of effort and a lot of money are going into the valuation of options and other financial derivatives, and that this equation this Black-Scholes equation beautifully produced the heat equation. And additional correction terms will produce a convection diffusion equation. So this is a application that we wouldn't have made some years ago, but now it's worth having focusing on that. I think it's interesting in itself. And then, so this is what's coming, and then you could say one-way wave equations, but nonlinear. So nonlinear wave equations, and those are called conservation laws. Okay, now that's after these linear cases. All right, so I'm ready to tackle the heat equation. Starting then on to the next section of the notes. Okay, so let me tackle it here. So the heat equation. Let me take the constant to be 1 ut equals uxx. Okay. Because we already see the big difference now. There's a second x derivative, but only a first derivative in time. The dimensions of t and x are no longer the same. We won't have delta t and delta x comparable. Now it will be delta t comparable with delta x squared. And that's a very significant difference, because that's, if delta x is small, delta x squared is extremely small. So when delta t has to be, is constrained by delta x squared, we're looking at small time steps. We're looking at stiff systems. Absolutely. This is going to be a stiff problem, because the low frequencies and the high frequencies differ enormously in the decay rate. In fact, why don't we see it right away, starting as always with exponentials. So if I plug in u of x and t is some g of t e to the I kx, separating variables as always. Look for a pure exponential solution. Plug that in, we get dg dt times e to the I kx on the left. And now I have to take two x derivatives. So that brings ik down twice. So that's minus k squared, I squared giving the minus 1, times g times e to the I kx. And now, of course, I can cancel that, which is never 0. And I've separated out the time part. The g part, dg dt is minus k squared g. So g is e to the minus k squared t. Notice that it's k squared. And notice that it's real and negative. See, that's a very big difference. Compare e to the I kt, which it was for the one-way wave equation. The difference is enormous here. That's magnitude 1 energy conserved. This is magnitude smaller than 1 energy dissipated. This, we had a ratio delta t over delta x. Now we're going to see delta t over delta x squared, because somehow x and t are now have it's x squared that matches t now. Okay. So now when I put that into here, let me just do it. G of t is e to the minus k squared t. So there's the pure exponential. Simple as always, because we have constant coefficients, but highly informative. I guess another thing that I read off of that is what frequencies are decaying fast? High frequencies. If k is large, k squared is very large, and e to the minus k squared t is decaying very quickly. So high frequency, noise in the system, roughness, discontinuities are going to get smoothed out strongly by moving forward in time. And physically what's happening is we have like our wave front, which stayed a perfect step function in the wave equation, will instantly smear. So diffusion smears discontinuities. Heat travels. If we were back over here, if the temperature starts out as 1 on this side and 0 on this side, then in an instant, some heat flows from right to left. In fact, it flows with infinite speed. In a short delta t, there's a little heat all the way out there. Very little, of course, because it's, well, I guess we want to see what that behavior is. So I now want to write down, staying with the differential equation, what do we want to do? We did the exponential case and learned a good bit from that, the fast decay of high frequencies. But now comes the next step would be to put different frequencies, different k's together. By linearity, we can add these solutions. We can multiply by any, we can multiply that by any numbers we want depending on k. We still have solutions, and we can integrate over k. So we will, actually. That will be the next step. Let me write down what that does. I'm going to take a little jump here to put on the board what I just said in words. I can multiply this e to the minus k squared t, e to the ikx. That's what's happening to the pure frequency k. If I multiply that by the amount of that frequency, which is in the initial condition. So here's the initial condition, u0, and I've taken its Fourier transform. This tells me how much of frequency k is in the problem, is in the initial problem. This tells me how much of frequency k is in the initial problem. That amount multiplies this with this rapid decay as time goes forward. But at any later time, I'm just adding up. And since k, we're on the whole line, k is continuous. So we add up from k equal minus infinity to infinity. And I think we have to remember the 2 pi that depends on our particular definition of the transform, but I'm going to stay with this one. That's the answer. That's u of x and t. So I've said that in words, but actually we could just check it. We would like to know that this left-hand side solves the heat equation, and we would like to know that it has the correct start, the correct u of x and 0. Well, let's check that. At t equals 0, at the start, this is 1. So at the start, this formula, without that thing there, is just the inverse Fourier transform that takes the Fourier transform, multiplies by this, integrates to recover u0. So it does start out correctly. Should I say that again? It starts correctly because at t equals 0, this is just the inverse Fourier transform of u0, so it produces u0. It inverts this transform that we took. Secondly, does it solve the heat equation? Sure, because for each k, we've just found that that solves the heat equation, and now we're just putting different k's together. So that's the answer. So you might say, okay, perfection. We don't, do we need finite differences? Well, I guess we do. This is typical of formulas that give the answer exactly, but in terms that are not numerically convenient. Because look what we have. To use this formula, first of all, this requires an integral, an infinite integral. To find, integral to find for u naught, u hat, we would have to use this formula, we'd have to find this transform, and then we have to do this integral for the inverse transform, this integral for the answer, u. Two infinite integrals. And not to mention the fact that on a finite interval, when x doesn't go all the way from minus infinity to infinity, the formula, we have to think all over again. So we have a nice formula for the answer, but it looks nice, but it's not numerically terrific. We can get a lot of information out of this. And there's one other special solution that's also extremely informative. What if, so I'm going to do a special case, but it's the big case. What if the initial condition is a delta function? What if the initial condition is a delta function? An impulse at time 0, x equals 0, an instant source of heat at a point source with finite strength, you could say, an impulse at time 0. For the wave equation, what happened? That was like turning on a flash of light, and it went along the characteristics. For the heat equation, it'll be quite different. There aren't characteristics here. But this is an extremely important solution, and I think you could call it the fundamental solution to the heat equation. You may know what it is. You may have seen this formula. It's fantastic that we get a formula for this one. Well, you could say, we've got a formula. What's the Fourier transform? What's u naught hat of k for the delta function? 1, right? The Fourier transform of the delta function is a constant, 1. All frequencies are there in equal amounts. This is a constant, so I can remove it. It's 1. And I'm left with a specific integral to do. And the question is, can I do it? And the answer turns out to be yes. you can do that integral with when this is a constant, and that will give you the answer with that starting value. And let me just say what that answer is. U of x and t, this is the fundamental solution. U fundamental, maybe I should say, because it's such an important case, turns out to be, well, it's not obvious what that integral is. And by the way, normally, let's see, normally it's, we take a kind of, to get the answer that I'm going to write down, we take a kind of end run on the integral. And I'm going to take a serious end run and write down the answer exactly. Here's the key part of the answer. A solution which starts from a delta function spreads, of course, and the shape as it spreads is a bell. It's the famous bell-shaped Gaussian distribution of e to the minus, so is it e to the minus x squared, I guess? And then always here comes that scalar tells us the width of the bell. How far has it spread at time t? And what goes there is 4t. That's the key observation. And notice how x squared and t are coming in. It's that ratio x squared to t that's crucial. That's the parameter here. And of course we need to multiply by a constant. And how do I know I need a constant? Because the total heat is conserved. So in other words, the integral of the delta function, the original source of heat, was 1. The integral from minus infinity to infinity of the delta function, which is all totally concentrated at one point, is 1. So I need to put on whatever constant it takes so that the integral of this thing shall stay 1 for later times. This is one integral from minus infinity to infinity that we can do, and it turns out to need 1 over the square root of 4 pi t. That solves the heat equation. Well, it's not a lot of fun to plug that into the heat equation, but it's possible, right? The x derivative, the time derivative is going to be messy. It'll have 2 terms. The x derivative will have 2 terms, and they'll agree. Yeah. And the notes will give one way to do the integral and get that answer. You see that integral, it's integrals with e to the minus k squared in them are usually impossible on a finite interval. But here we're going all the way from minus infinity to infinity, which you might think makes the problem harder, but actually it makes it a great deal easier, and we can get an explicit answer, a beautiful answer. So we learn that the solution to the heat equation is coming from a point source, is a bell-shaped Gaussian curve that gets wider and wider as t increases. But I guess you would want to look to see, well, what happens as t comes down to 0? Does that really approximate? I'm meant to say, does it really converge to? This should, as t goes to 0, this should go to the delta function. And in some way it does. In some way it does. It's wonderful. The delta function, of course, is 0 away from the origin. So why does this approach 0 away from the origin? Suppose x is 1. Suppose x is 1. Then, do you see this thing going to 0 as t goes to 0? Look what's happening. As t goes to 0, this part is blowing up, but kind of weakly. That's not a disastrous blow-up. Compared to this e to the minus, let's say, 1 over 4t, as t goes to 0, that's e to a very negative exponent. That's going to 0 very fast, much faster than this is going to 0. So if you like to think of L'Hopital's rule or ratio or something, this quantity is going to 0 way faster than this one is, and the result is 0, except at the 1 point x equals 0 where this is 1, and the fact that the total amount of heat stays at 1 tells us that the delta function is the limit there. Okay, so that's, today was the heat equation continuous case with these explicit answers. And then next time is, tomorrow I guess, is the heat equation finite differences. And again, we'll have several difference methods, and to compare them would be terrific. So maybe that, please think about that comparison with the heat equation, and or what I was saying at the beginning of class, a deeper look at the comparison for the wave equation. Okay, so see you tomorrow for difference equations for this problem. Thanks.